All right, so here's a different way of sorting a list. This sorts a list quickly, and the algorithm is called quicksort. And what we do is this. If you give me a list that is either the empty list or a list containing one element, then it's already sorted, okay? So right here, right? Think of those as the base cases. In fact, I needed two base cases, length 0 or length 1, okay? Now then I'm going to split my list into two sublists. These are the lists that have small values of x, okay? And what I mean by small values of x, the ones that are smaller than the very first element on the list, right? So my list looks like A1, A2, and so on, right? And what I'll do is I'll split it, and I get everything that is smaller than N1. That's one list. Actually, I'm sorry, not less than or equal to, just less than. And then another one that has everything that is greater than A1. Okay, that's how I split those. And then what I'll do is I'll sort the ones that are small. I'll sort the ones that are big, right? Then I'll put the sorted version of the small ones in front, and then I put the ones that are equal to A1, and then I put the sorted version of the ones that are bigger than A1, and sure enough, that should be my list, sorted. So here's a recurrence relation. A1 is equal to 1, because if I only have one element on the list, then I just come through here and I go, what's the length? Oh yeah, it's less than or equal to 1, return it, okay? A2, or rather AN, well, I have to sort the small ones and I have to sort the big ones, right? So I have to do two calls to sort. That's where the 2 times is coming from. And I'm sorting lists that are basically about half as large. So that's A of n over 2, okay? And then I have to somehow combine them, right? So that combining is going to be about as long as the original list. So that's n steps for that, okay? Now, realize that this only works when n is a power of 2, because saying 2 of an divided by 2, if I have 7, then I say 7 divided by 2, oh crud, that's 3.5. So this really only makes sense when n is a power of 2, but that's okay, right? So when n is a power of 2, this is a nice recurrence relation for this. So let's try to solve our recurrence relation. A sub 1 is equal to 1, A sub n is equal to 2, an over 2 plus n. Let's try to solve it. Well, unfortunately, nobody's come through and told us what the solution is. So we're going to have to guess. One of the ways that I guess is by kind of, just writing down some elements of the sequence. So A1 is equal to 1. We're given that. So how about A2? Well, that's 2 times A1 plus 2. That's 4. I'm going by powers of 2. So how about A sub 4? Okay, so that's 2 times A sub 2 plus 4. That's 12. A sub 8, A sub 16, and so on. Here's kind of a nice set of input values, right? So I have n, I have a sub n, then I have n squared. So I think you can see that a sub n is growing faster than n, right? I mean, n got to 16, a sub n is already up to 80. That's 5 times bigger. But it's not growing as fast as n squared. So something that is between n and n squared. And just a wild guess, whenever I'm looking for something between n and n squared, I say, how about n log n? So that would be 0, 2, 8, 24, 64, 160. You know what? It's not conclusive, right? I mean, it looks like a sub n is a little bit bigger than n log n. On the other hand, it doesn't seem to be growing much bigger than n log n. So maybe they're growing about the same rate. It's just so let's try to prove that. Okay. So what I'm going to prove, and in this case, I've taken enough rounding that I can't say equal. So I need to say less than or equal to, right? But a sub n is less than or equal to 2 times n log n. Okay. So let's try that. Let's do the base case is equal to n is equal to 2. Okay. And I need, greater than 1, because log 2, or rather log 1 is 0, and I'm not going to get anything with that, right? So let's just do n greater than 1. So the base case is n2 as opposed to 1. Okay, so what's a sub 2? Well, from definition, that is 4. Okay. And that is actually less than 2 times 2 log 2, right? Because log 2 is just 1, and that's 2 times 2, that's 4. So yeah, I get less than or equal to, okay? So this just comes from right there, right? A sub 2 is 2 times a sub 1 plus 2. So that's 2 times 1 plus 2. So yeah, check mark, right? That works. There's our base case. Now suppose that n is greater than 2. Then a sub n is equal to 2 times a sub n plus 1. This is just the definition, right? Or perhaps I should say the recurrence relation, right? That's where that comes from. And now I say, oh, that's less than or equal to this, okay? I have to say less than or equal to because that's my induction hypothesis, right? So this fact is just because of the induction hypothesis, okay? All right. After that, it's just algebra, right? Once we have opened up the recurrence relation, once we do the induction hypothesis, the rest is algebra. So that's actually equal to 2 times n log n over 2, and that's because this is 2 times n over 2 log n over 2. So yeah, that's just the 2's canceled, okay? And once I have it written like this, then I can actually write that as 2 times n log n minus 2n. How come? Well, log of n over 2 is what? It's log of n minus 1, right? So log of n minus 1 times 2n, 2n log n minus 2n, okay? The minus 2n and the plus n combine, so I have 2n log n minus n. And again, I get a less than or equal to term because I'm subtracting something from 2n log n. So 2n log n is actually larger than the previous one, right? So as long as I have the inequalities in the right direction, all this goes through, and that's my induction step. So this is actually something that you probably knew about sorting. Things like insertion sort, which is basically what our last sorting mechanism was, they tend to take n squared. It's actually hard to come up with a sorting algorithm that takes longer than n squared, right? But you can sort faster than that. And this is an example of a sorting routine that sorts faster than that. It sorts in n log n time. You actually can't do any better than that. That's as fast as you can get, at least when you're using comparisons, okay? So anyway, that was quicksort.